All right, so the goal of this video is to discuss three important types of integral domains, namely Euclidean domains, principal ideal domains, and unique factorization domains. And we'll define what all these things mean in this video. So first, we'll start with some motivation. We might have noticed at this point that there are some similarities between the ring of integers z and the ring of polynomials f bracket x, where f is a field. So what similarities do they share? Well, one, we might notice that they both have some sort of division algorithm. Two, one thing we can show is that every ideal in both of these rings is principal. And as a reminder of what that means, it means that every ideal is generated by a single element. So if I give you an ideal I can find an element of I that generates the whole ideal. Three, we might notice that these are unique factorization domains, right? Z, we always have a unique factorization into products of primes. F bracket x, we have unique factorization into a product of irreducibles. And so the natural question to now ask is, what other rings share these properties? Well, the first thing I want to kind of mention, we'll prove this later, but this might be a good exercise to try, so it might be a good place to pause and try this problem. For property 2 in Z, what we can do is we can start with an ideal I. And if I is just the ideal containing 0, then we know I is generated by 0. If I is not a 0 ideal, then what we can do is we can use well ordering to choose the smallest positive element of I, call it D, and show that I is the ideal generated by D. So hint, use the division algorithm. So if you want to try this exercise, go ahead and try it. If not, we're going to prove this in more generality in a little while. So for the remainder of this video, we're going to assume that R is always an integral domain. A lot of these definitions do work for commutative rings, but just for convenience, we'll work with integral domains because a lot of the structures we'll be studying will be based on integral domains. Okay, so the first definition is we'll say let A and B be an R and B be non-zero. We'll say that B divides A. We're going to borrow the definition from the integers. So we'll say B divides A if there exists an integer C, or rather a ring element C, such that A is equal to B times C. And we'll write B divides A in the following way. So it's the same notion as with the integers, or the same definition as division. We'll call an element U in R a unit if it's invertible under multiplication, right? So the idea is that U is a unit if there exists some V in R such that U times V is equal to 1. And integral domains are commutative rings, so we get that V times U is equal to 1 for free from this definition. And finally, we'll say if A and B are ring elements, we'll say that A is an associate of B if A is equal to B times U for some unit U in my ring. So this is going to be the notion of associate. It's the same as the notion for polynomial rings, except now we're just generalizing it to an arbitrary integral domain. And let's look at a few examples. So the first kind of boring example that we've already seen is that the units in Z are 1 and -1. These are the only integers that are invertible under multiplication, namely 1 times 1 is equal to 1 and -1 times -1 is equal to 1. And if I take any other integer, I cannot multiply it by an integer to get 1 back. For example, 2 times an integer will never be 1. So 2 is not a unit. Okay, and then I can ask, what are the associates of any integer? Well, I just take that integer and multiply it by my 2 units. So for example, if n is an integer, its associates are n and -n. Okay, so now let's look at another example. If we look at the ring f bracket x, we showed in an earlier video that the non-zero constant polynomials are the units in my ring. So these are just the non-zero constants. And if f of x is a polynomial in capital F bracket x, its associates are just the units times that polynomial. So they're just the constant multiples of f of x. So if you're working with, say, r bracket x, r being the real numbers, then any polynomial has any non-zero polynomial has infinitely many associates. I could take that polynomial to multiply it by any non-zero real number and get an associate of my original polynomial. Okay, so now let's consider a slightly more interesting example. So I'm going to consider the ring z bracket square root of 5, and these are all elements of the form a plus b root 5, where a and b are integers, and this is a subring of the real numbers. Okay, so why is this ring weird? Well, first of all, we'll notice that the units of this ring are not just 1 and -1 like with the integers. There are some weird units, and as a consequence, we'll see that certain elements are associates that we wouldn't expect to be associates when just glancing at them. So what do I mean? Well, first thing I might notice is that 1 plus square root of 5 divides -4. And that's the case because -4 can be written as 1 plus root 5 times 1 minus root 5. So if we expand that out, we'll get -4. Okay. We'll notice that 2 plus square root of 5 is a unit. Why? Well, 2 plus square root of 5 times -2 plus square root of 5 is equal to 1. So 2 plus root 5 has a multiplicative inverse. In fact, 2 plus root 5 and -2 plus root 5 are both units because they have multiplicative inverses. Okay, and where does that lead us? Well, I'll notice that -2 is an associate of 4 minus 2 root 5. Why is that the case? Well, -2 is 4 minus 2 root 5 times a unit, 2 plus root 5. So we'll see that these two elements are associates. So a lot of these rings do get kind of weird after a while. But that's kind of what makes this whole general picture more interesting. Okay, so now we're ready to prove some simple facts that we'll find useful throughout the rest of this video. The first simple fact will be that if I have a unit in my ring, then that unit divides every other element A and R. So I'll just write if U is an R and is a unit and A is any other element of R, then U divides A. So units divide everything in our ring. Another thing that's kind of obvious is that A is an associate of B if and only if B is an associate of A. So this will be a quick proof. And then finally, if I take a non-zero element of my ring, then this element is divisible by its associates. Okay, so let's prove this. So let's start with 1. So I'll say, suppose that U and R is a unit, right? Then what I know is that U times V is equal to 1 for some V and R. And where does that lead me? Well, I can multiply both sides by A now, right? So I can say then UV times A is equal to 1 times A, which leads me to, on the left-hand side, I'll use associativity. I'll write this as U times VA. And on the right-hand side, I'll just use the fact that 1 times A is equal to A, which leads me to the fact that U divides A. Okay, so that proves 1. 2 is also pretty simple. 2 is really just saying that if A is equal to B times U, then, well, not even then, if A is equal to B times U, this is true if and only if A times U inverse is equal to B. Okay, and 3 is also pretty straightforward. I'll say, suppose that A and B are an R, and I guess suppose that these guys are non-zero, and A is an associate of B. Okay, well, where does that lead me? That means that A is equal to B times U for some unit U and R. Well, what does that mean? That means that A times U inverse is equal to B. In other words, that A divides B. Okay, and so that finishes the proof of this proposition. Okay, so the last idea that we want to generalize from Z and from F bracket X is this notion of an irreducible element. So what do I mean by this? Well, I'll say a non-zero element P in R is called irreducible if its only divisors are units and associates. So where's this definition coming from? Well, if you think about Z, following this definition, the irreducibles are just going to be the prime numbers. The reason being that the only divisors of prime integers are plus or minus 1 and plus or minus p. And if I think about this, plus or minus 1 are the units in Z. Plus or minus p are the associates of p. So we're what we're doing here is we're generalizing our notion of prime number to an arbitrary integral domain. Okay, so now we're ready to prove a basic fact about irreducibles. So I'll let P be an element of R, it'll be a non-zero element, and we're going to show that P is irreducible if and only if whenever I factor P as A times B for some A and B and R, then either A is a unit or B is a unit. So let's start this proof. So I'll suppose that P is irreducible and P is equal to A times B. Well, one thing I might notice is then I know that A divides P. Okay, so by definition, since P is irreducible, I know that A is a unit or an associate of P. Okay, if A is a unit, then we're done. There's nothing to show because we've shown that A is a unit. So I'll suppose that A is not a unit, and also suppose that A is an associate of P. Well, what does that tell me? That tells me that then A is equal to P times U for some unit U, right? So for some unit U in R. Okay, so where does that lead me? Well, then what do I have? I have P is equal to AB, and I know that A can be written as P times U. So this is going to be P times U times B. And so what am I looking at? I'm looking at P is equal to PUB. And one thing to recall about integral domains is that I have cancellation, right? So I can cancel non-zero elements from both sides. So I can cancel out these P's, and I end up with 1 is equal to U times B. So what does that tell me? It tells me, hence, B is a unit. Okay, and I've proved the forward direction. And finally, we'll go in the backwards direction. So our goal now is to show that if I have a divisor of P, then that divisor is either an associate or a unit, right? I want to show that if P has this property on the right-hand side, then P is irreducible. So I want to take a divisor. I'll say suppose A divides P, and my goal is to show that A is either a unit or an associate. Okay, so suppose A divides P, then I can say that P is equal to A times B for some ring element B in R. Okay, well, by our property, we know that A is a unit or B is a unit, right? One of those has to be true because this is our assumption, right? Namely, this thing in the red box right here. Well, if A is a unit, then I'm done. If B is a unit, then I have that A is an associate of P. Why is that the case? Well, it's because, again, I have P is equal to A times B, and I could write A as P times B inverse. So I have that A is an associate of P. Okay, and that finishes my proof. Okay, so now we're ready to define the notion of Euclidean domain. So we'll say an integral domain R is called a Euclidean domain if there is a function delta from the non-zero elements of R to the natural numbers, and we call this the Euclidean function, and it satisfies two conditions, and these two conditions will become apparent in a second. Well, the first condition is that if A and B are non-zero elements, then delta of A is less than or equal to delta of A times B. And the second condition is the division algorithm. So if A and B are ring elements and B is non-zero, then there exists Q and R in my ring such that A is equal to BQ plus R and R is equal to 0, or delta of R is less than delta of B. So a Euclidean domain is really just an integral domain that has a suitably defined division algorithm. So what are some examples? Well, the integers are a Euclidean domain where I define delta of A to be the absolute value of A. So let's check this. The first condition, we might notice that delta of A is equal to the absolute value of A. Well, absolute value of A is just absolute value of A times 1. I know that 1 is less than or equal to the absolute value of B for any non-zero integer B. So absolute value of A times 1 is less than or equal to absolute value of A times absolute value of B. But this quantity is just equal to absolute value of AB, which is delta of AB. So we have our first condition. For our second condition, if B is non-zero, then I know that I can write A as the absolute value of B times Q plus R. So one thing to recall is we've only proved the division algorithm for positive values of B. So the absolute value of B is always going to be positive, and I have A is equal to the absolute value of B, Q plus R, and either R is equal to 0 or R is greater than 0 and less than the absolute value of B, i.e. the absolute value of R is less than the absolute value of B. Okay, but So one thing I'll say again is that we proved this for b positive. What if b is negative? Well, if b is negative, this is actually pretty simple. If b is negative, we can actually write a as b times negative q plus r, and we'll notice that the absolute value of r is less than the absolute value of b, or r is equal to 0. So notice that this condition says that delta of r is less than delta of b, or r is equal to 0. Okay, so Z is a Euclidean domain. Okay, so another example of a Euclidean domain is the ring of polynomials f bracket x, where f is a field. And what I'm going to do is I'm going to say delta of a non-zero polynomial is just the degree of my polynomial. Okay, so we've already shown that condition 2 holds, right? That's just our division algorithm from f bracket x. We did that in an earlier video. So let's check that condition 1 holds. And we've already kind of done this too, but let's double check it. So I'll take two non-zero polynomials, f of x and g of x, in f bracket x, and what I'm going to notice is that delta of f of x times g of x, well, that's just the degree of f of x times g of x. I know that that's the degree of f of x plus the degree of g of x, and that's greater than or equal to the degree of f of x because the degree of g of x is either 0 or larger. And then finally, I noticed that this is just equal to delta of f of x. So I get that f bracket x is a Euclidean domain as well. Okay, and finally, 2 more examples of Euclidean domains, and we'll leave the proofs of these for different videos because these proofs tend to be a little bit more involved. So the first is the ring Z bracket I of what are called Gaussian integers. So these are elements of the form A plus BI, where A and B are elements of Z. Right, so these are complex numbers whose real and imaginary parts are integers, and we define delta of A plus BI to be A squared plus B squared. So these are called the Gaussian integers. And we also have the Eisenstein integers. So these are the integers Z, or elements of the form Z bracket omega. These are A plus B omega, where I've defined delta of A plus B omega to be A squared minus AB plus B squared, and where omega is a primitive cube root of unity. So for example, we can take omega to be e to the 2 pi I over 3. So all that means is that omega cubed is equal to 1. Okay, and one thing I'll note here is, why is there no omega squared present? Well, one thing about cube roots of unity, or primitive cube roots of unity, is that omega squared plus omega plus 1 is equal to 0. So that omega squared, anytime we encounter that, we can replace it with minus 1 minus omega. So these are 2 more examples of Euclidean domains. And again, we'll omit the proofs here because they're quite involved and they'll get their own videos. Okay, so the next type of important ring that we're going to encounter is what's called a principal ideal domain. So I'll let R be an integral domain, and I call R a principal ideal domain. We'll abbreviate it as PID if every ideal I of R is principal. So let's recall what that means. This means that if I take an ideal I, that's a subset of R, then there exists an element B in I such that I is equal to the ideal generated by B. So a principal ideal domain is one in which, where if I take an ideal, that ideal is always generated by a single element. And so our very first theorem is going to show that every Euclidean domain is a principal ideal domain. So if R has a division algorithm, then every ideal of R is principal. Okay, so let's prove this result. So I'll start our proof with let I be a subset of R be an ideal. The first thing I'll note is that if I is just the 0 ideal, so I is just the set containing 0, then I is the ideal generated by 0. So there's really nothing to show here. The one element ideal containing 0 is principal. Okay, so the more interesting thing happens when we look at non-zero ideals. So I'll suppose that I is a non-zero ideal. And what I'm going to consider is I'm going to consider the following set. I'm going to let S be the set of delta of I such that I is a non-zero element of my ideal, right? And what I know is that this is a subset of the natural numbers. Moreover, I know that this is a non-empty subset of the natural numbers because I know I is not the 0 ideal, right? So there are some non-zero elements in I, and so there are some values of delta I that land in the naturals. So what I'm going to do is I'm going to say let B be an element of I such that delta of B is the smallest element of S. So the smallest element of S, right? So by well ordering, S has a smallest element, some delta of B. And so I'm going to pick one of those B's that give us the smallest element of S. Okay, so what does that mean? In other words, delta of B is less than or equal to delta of I for all I in my ideal I. Okay, the first thing I'll notice is that, well, B is an element of I immediately gives us that the ideal generated by B is a subset of I, right? If B is an element of I, then every multiple of B, every R multiple of B has to be an I. So that means the ideal that B generates has to be a subset of I. Okay, so we have that. Our goal is now to show that I is a subset of B, of the ideal generated by B. Okay, so I'll say consider some element A in I. Well, since we're working with a Euclidean domain, I could say then there exist Q and R in my ring such that A is equal to BQ plus R, and either R is equal to 0 or delta of R is less than delta of B. Well, what does that tell me? Then the element R, which I can now write as A minus BQ, let's think about this. I know that A is an element of I. I know that BQ, well, B is an element of I, so BQ has to be an element of I. So I have that R is an element of I, and either R is equal to 0 or delta of R is less than delta of B. The thing that I'll notice right away is that this one is impossible. So this is impossible since delta of B is minimal, right? This is the smallest possible delta value that's given by an element of I, right? So I know that R is an I. It's impossible for delta of R to be less than delta of B because delta of B is minimal. So it must be the case that R is equal to 0. So what can I say? Well, hence, I know that A is equal to BQ. In other words, A is an element of the ideal generated by B. So I've shown that I is a subset of B. And where do we go from here? Well, I know that I is a subset of the ideal generated by B. I know that the ideal generated by B is a subset of I. And so I is equal to the ideal generated by B. Okay, so this is kind of neat because if we have a suitably defined division algorithm, we can show that every ideal in R is a principal ideal. Okay, so now that we've established this theorem, I'd like to point out that the converse of this theorem is actually false. It is not true that every PID is a Euclidean domain. And there's an example that's a bit tricky to prove, but I'll write out the example anyway. So the converse of this theorem is false, and the ring Z bracket 1 plus the square root of negative 19 all over 2 is an example of a ring that is a principal ideal domain, but is not a Euclidean domain. So this does not have a division algorithm in the sense that we defined above. And one thing I'll point out is that the proof of this is not easy. And again, this is one of these things that would require its own video. So we'll omit the proof for now. Okay, and so now our final goal for this video is to show that every PID has the property of unique factorization. So every PID is going to be what's called a unique factorization domain. So I'd like to show that every element of a PID can uniquely be factored into irreducible. So this is kind of generalizing our fundamental theorem of arithmetic. Before we get there, though, we have to prove a series of lemmas. So let's start with the first lemma. And these are all pretty straightforward. So the first lemma has 3 parts to it. And so I'll take A and B and R. So R is an integral domain throughout. I'll say that the ideal generated by A is a subset of the ideal generated by B, if and only if B divides A. From that, we'll actually have a quick consequence. We'll have that the ideal generated by A is equal to the ideal generated by B, if and only if A divides B and B divides A. And then finally, the ideal generated by A is properly contained in the ideal generated by B. So they're not equal. A is a strict subset of B, if and only if B divides A and A and B are not associates. So this will be our first lemma. So let's prove this. So I'll start with 1, and I'll start with the forward direction. I'll say, suppose that the ideal generated by A is a subset of the ideal generated by B. Well, what do I know? I know that then A is in the ideal generated by A, which is a subset of the ideal generated by B. So A is an element of the ideal generated by B. Thus, this tells me that A is equal to B times C for some C and R, right? Because the ideal generated by B are all the R multiples of B. So that means A is a R multiple of B. But what does this tell me? I could say hence B divides A, right? I've written A as B times C, and this is just our definition of B divides A. Okay, great. So let's go backwards. All right, so now I'll suppose that B divides A. Well, then I know that there exists an element C in R such that A is equal to B times C. Okay, I need to now show that the ideal generated by A is a subset of the ideal generated by B. That is, every multiple of A is a multiple of B. Okay, so let's do that. I'll say let X be an element of the ideal generated by A. Then I know that X is equal to A times R for some ring element R. Well, what does that give me? So I have X is equal to A times R, and now I can rewrite A as B times C. So this is BCR. Using associativity, this is B times CR, and I see I have an R multiple of B, so this is an element of the ideal generated by B. So hence, I've shown that the ideal generated by A is a subset of the ideal generated by B. So that finishes the first part of this lemma. Part 2 of the lemma is actually just a quick application of part 1. So let's prove 2. So we have that the ideal generated by A is equal to the ideal generated by B if and only if the ideal generated by A is a subset of the ideal generated by B, and vice versa. Well, what does that mean? If I apply part 1, right, if I apply part 1, I know that this is true if and only if B divides A and A divides B, and so we've proved 2. Okay, and finally we're ready to prove 3, and we'll do this pretty quickly. So I'll suppose that so we'll go in the forward direction first. I'll suppose that the ideal generated by A is a proper subset of the ideal generated by B, and for contradiction, I'll suppose that A and B are associates, right? The idea being that I know that if A is a subset of B, then B divides A, so we'll assume that A and B are associates. Well, what does that tell me? It says then I know that AU is equal to B for some unit U and R, but what does that tell me? Then that tells me that A divides B, and what does that mean? In other words, this tells me that B, the ideal generated by B, is a subset of the ideal generated by A, and this is a contradiction. Okay, so that finishes the forward direction. Now let's clean up and do the backwards direction. Okay, so now I'll suppose that B divides A, and I'll assume that A and B are not associates. Well, since B divides A, we can immediately say that the ideal generated by A is a subset of the ideal generated by B. Okay, so now what we want to show is that it's impossible for them to be equal to one another. So if they are equal to one another, if the ideal generated by A is equal to the ideal generated by B, then I know by 2 that A divides B and B divides A, right? So I can write that A, or rather B is equal to A times C, and A is equal to B times D for some elements C and D in my ring. Okay, and where does that get me? Well, I have that then A is equal to B times D, and I know that B can be written as A times C, so A can be written as ACD. Well, where does that get me? I have that A is equal to ACD, and since I'm working in an integral domain, I have a cancellation law. I can cancel out these two A's. So this tells me that 1 can be written as C times D. In other words, C and D are units. And so, well, if I look up here, if C and D are units, this tells me that A and B are associates. But what's the problem? We're assuming that A and B are not associates, so this is a contradiction. So I can say, hence, the ideal generated by A is not equal to the ideal generated by B, and so the ideal generated by A is properly contained in the ideal generated by B. So that proves my first lemma. Before we get to our next lemma, we need to motivate an example. So I'm going to motivate something called the ascending chain condition. So let's consider the ring Z, and let's consider the integer 36, right? And we know 36 has the unique factorization 2 squared times 3 squared. Okay, so I know that the divisors of 36 are numbers like 36 and 18 and 9 and 12 and 3 and 2 and 4 and 1, right? Those are the divisors, and those divisors are made up of the prime factors, or some combination of these prime factors that occur in the prime factorization of 36. Okay, so what can I notice? Well, let's consider the ideal generated by 36. One thing I might notice is that, well, every multiple of 36 is a multiple of 18. So we have this containment of ideals, right? And this is just using property 1 from the lemma that we just proved. Well, I know the ideal generated by 18, every multiple of 18 is a multiple of 9. I know that every multiple of 9 is a multiple of 3. I know that every multiple of 3 is a multiple of 1. And this is kind of where this stops, right? I can't go any further. So I have this kind of containment of ideals. And then you might ask, well, what if I started with something other than 18? What if I did 36? I know that this is contained in the ideal generated by 12. And maybe we can repeat some 12s, right? So this is all still true. And then maybe at some point I might skip down to 6 and repeat the 6 once. And this is contained in the ideal generated by 2. I could repeat the 2 a bunch of times, but eventually, what do I notice? I notice that either these ideals are going to stabilize at some factor of 36, or they're going to go all the way down to 1 and stabilize at 1, right? But the idea is that we can't ascend infinitely, right? We're always going to ascend, and the highest point we can reach is the ideal generated by 1, which is all of the integers, right? I can also do something like the ideal generated by 36 is a subset of the ideal generated by 6, is a subset of 3, is a subset of 3, is a subset of 3, so on and so forth, right? The point is that after a while, I'm going to start repeating the same ideal over and over and over again, right? So I know, like, the ideal generated by 6 is properly contained in the ideal generated by 3, but at some point my ideal has to start repeating whether I reach 1 or whether I don't reach 1. Okay, so this is going to motivate our next definition. Okay, and so here's our definition for the ascending chain condition. I'll say that a ring R satisfies the ascending chain condition, and we'll just abbreviate this as ACC, if whenever I have a chain of ideals, the ideal generated by A1 is a subset of the ideal generated by A2, so on and so forth, going upwards, for some elements A1, A2, A3, so on and so forth in R, then there exists some natural number n such that the ideal generated by A1, AI, is equal to the ideal generated by an for all I greater than or equal to n. So this is telling me that eventually I get to a point where I'm just repeating the same ideal over and over and over again, right? All the ideals have to stabilize at one ideal. Okay, so now we'll prove that every PID, every principal ideal domain, satisfies the ascending chain condition. So what I'm going to do is I'll start with an ascending chain of ideals in my ring R. So I'll say for some A1, A2, A3, so on and so forth in R. And again, R is going to be my PID. Okay, so what I'm going to do is I'm going to union all of these ideals together. I'll say let I be the union of the ideal generated by the AIs, where little I goes from 1 to infinity. Okay, the first claim that I'm going to establish is that the set I've just created I is an ideal of R. Okay, well, the first thing that's obvious is that I is not empty, right? All of these ideals, the ideal generated by A1, for example, contains 0. So 0 ends up inside of that union. So now to show that I is an ideal, what I need to do is I need to show that I is closed under subtraction, and I need to show that I absorbs elements of R under multiplication. So let's check that. So I'll say, let A and B be elements of I. We'll check that it's closed under subtraction first. Well, what do I know? I know that then A is an element of the ideal generated by AK, and B is an element of the ideal generated by AJ for some, well, J and K that are greater than or equal to 1, right? Without loss of generality, I'll assume that J is greater than or equal to K. Well, what does that tell me? Then I know that the ideal generated by AK is a subset of the ideal generated by AJ, right? This is an ascending chain. So I know that A is in the ideal generated by AJ. Well, what does that tell me? Well, thus A and B are in the ideal generated by AJ. So since that's an ideal, I know that A minus B is in the ideal generated by AJ. Hence, I know that A minus B is in the union of these ideals, which is just my set I. So I see that I is closed under subtraction. So now let's check that I absorbs elements of R under multiplication. So I'll say let I be an element of little I, and, well, let's call this element A. So I'll say let A be an element of little I, and R be an element of my ring. Well, then what do I know? I know that A is an element of AK for some K bigger than or equal to 1. Well, what does that tell me? I know that the ideal generated by AK is an ideal. So I could say then RA and AR are elements of the ideal generated by AK. Hence, I know that RA and AR are elements of the union of these ideals, which is equal to I. So I've shown that I is an ideal of R. Okay, so now that I know that I is an ideal of R, let's use the fact that we're working in a principal ideal domain to show that we have the ascending chain condition. Okay, so what do we know? We have this ideal I, so I could say since R is a PID, there exists some element C in I that generates all of I, right? I know that I is a principal ideal. Okay, so I could say since C is an element of I, there exists an N in N such that C is an element of the ideal generated by AN, right? So what does this tell me? This tells me that C, the ideal generated by C, is a subset of the ideal generated by AN. And what does this tell me? This tells me that the ideal generated by C is a subset of the ideal generated by AI for I bigger than or equal to N. So I'm just using the fact that I'm working in this ascending chain up here. Okay, well, what does that tell me? Well, this is kind of clever because we know that the ideal generated by AN is a subset of the ideal generated by AI for all I bigger than or equal to N. That's just our ascending chain. So I need to show that the subset goes the other way. So how am I going to do this? Well, I'm going to have the ideal generated by AN is a subset of the ideal generated by AI, which is a subset of I, right? And just remember, this is the union of the ideals AI, where I goes from 1 to infinity. And what does this equal? Well, this is the ideal generated by C. And I see that this is and I already have established that this is a subset of the ideal generated by AN, right? So what I can do is I now have the fact that the ideal generated by AI is a subset of the ideal generated by AN, right? So I can say hence the ideal generated by AI is a subset of the ideal generated by AN. So what I've shown is that the ideal generated by AI is equal to the ideal generated by AN for all I bigger than or equal to n, and I've proved my ascending chain condition. Okay, so this is going to be our last lemma before we prove unique factorization for PIDs. And I actually really enjoy this lemma because the proof is super neat. So I'll say let R be a PID and P and R be irreducible. We'll show that if P divides B times C, then P divides B or P divides C. So if you recall, this is a property that we proved for prime integers, and we also proved this property for irreducible elements of f bracket x. One thing I'll point out is in ring theory, an element of my ring that has this property that whenever P divides B times C, then P divides B or P divides C is called a prime element. So in deeper ring theory, irreducibles and primes are different from one another. Irreducibles are elements of my ring whose only divisors are units and associates, and primes in my ring are elements that have this property that if P divides B times C, then P divides B or P divides C. So we've shown earlier that primes and irreducibles are the same in Z, and primes and irreducibles are the same in f bracket x. Okay, so let's prove this lemma. And why is this lemma so neat? So we're going to do something kind of funny. We're going to show that the ideal that P generates is maximal, right? So we show that the ideal generated by P is maximal. So how do we do that? Well, and we'll see why we do that in a second, but let's just write out this proof. So I'll say, suppose that I is an ideal, and I know that I is between P, the ideal generated by P, and my ring R. Okay, since R is a PID, I know that I can be written as the ideal generated by D for some element D in my ring. So what do I really have? I have that the ideal generated by P is contained in the ideal generated by D is contained in R. Okay, well, what does this tell me? It says thus, D must divide P, right? So this containment here, if you remember from our first lemma, this containment tells me that D has to divide P. Okay, well, since P is irreducible, we know that D is a unit or an associate of P. Okay, well, one thing is if D is a unit, this implies that the ideal that D generates is my entire ring, right? This allows me to show that one is inside of my ideal, and if one is inside my ideal automatically becomes my entire ring. And if D is an associate of P, well, this is going to imply that the ideal that D generates is the same as the ideal that P generates, right? So hence, what have I shown? I've shown that I is equal to the ideal generated by P, or I is equal to all of R. Okay, so I've shown that this ideal generated by P is maximal. Okay, so where does that lead me? Well, so now, since R mod P, since P is maximal, rather the ideal generated by P is maximal, I know that R mod this ideal is a field, but this implies that R mod this ideal is an integral domain, because I know every field is an integral domain. But if I have R mod an ideal is an integral domain, this tells me that the ideal generated by P is a prime ideal. Okay, and why is this useful? So now, if P divides B times C, then I know BC is an element of the ideal generated by P. So since I'm working with a prime ideal, I can then say that B is in the ideal generated by P, or C is in the ideal generated by P. And what does this mean? Well, this just says that P divides B, or P divides C. And that finishes my proof. So I really like that proof. I think that proof is really neat. Okay, so we're finally ready to define the notion of unique factorization domain, and we'll prove that every PID is in fact a unique factorization domain. So what is a unique factorization domain? So I'll start with an integral domain R, and I'll call R a unique factorization domain, or UFD for short, if any non-zero, non-unit element of R is a product of irreducibles. So that's the factorization part of the name unique factorization domain. What about the unique part? Well, the unique part says if I have two factorizations, P1 times P2 times dot 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 times PR, and Q1 times Q2 times dot 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 times QS, and they're equal for some irreducibles P1 through PR and Q1 through QS, then I have that R is equal to S. And moreover, after suitably reordering and relabeling these terms, we have that each PI and each QI are associates. So P1 is an associate of Q1, P2 is an associate of Q2, so on and so forth. So this is the notion of unique factorization domain. And we've already seen that Z is a unique factorization domain and F bracket X is a unique factorization domain. And now we'll show that every PID is a unique factorization domain. So the notion going on here is that we're working with some generalization of the fundamental theorem of arithmetic. Unique factorization domains are rings that have something like the fundamental theorem of arithmetic. All right, so we're finally ready to prove our last theorem, namely that every PID is a UFD. Every principal ideal domain is a unique factorization domain. And this proof is quite intricate, but it's going to be sort of similar to the proof of the fundamental theorem of arithmetic. Well, the uniqueness portion will be at least. Okay, so let's prove our theorem. So we'll prove the existence portion first. I'll suppose that A is an element of R and A is non-zero and not a unit. Okay, the first case to consider is that if A is irreducible. Well, if A is irreducible, then A is equal to A and we're done. We have a factorization of A into irreducibles, namely A is equal to A. So we'll assume that A is reducible. And what does reducible mean? That means A can be written as A1 times B1, where A1 and B1 are not associates of A and not units, right? And we'll assume that A has no factorization into irreducibles. So suppose I found an element that has no factorization. Well, again, what does that mean? A can be written as A1 times B1, where A1 and B1 are not units and not both irreducible, right? If they're both irreducible, then I have a factorization of A into irreducibles. So either A1 is not irreducible or B1 is not irreducible or both. Okay, well, moreover, either A1 or B1 don't have a factorization into irreducibles, right? If A1 can be factored into irreducibles and B1 can be factored into irreducibles, then I have a factorization of A into irreducibles. So it's got to be the case that either A1 or B1 or both don't have factorizations into irreducibles. So without loss of generality, I'll assume that A1 has no such factorization. And what I'll note is that the ideal generated by A is properly contained in the ideal generated by A1. Okay, because we know that A1 divides A, and I know that B1 is not a unit. So I know that A and A1 are not associates, and I know that A1 is not a unit. So I have this proper containment, and now I'm going to repeat the same argument, but starting with A1, right? I know that A1 has no factorization into irreducibles, so I'm going to write A1 as A2 times B2, and I'll get that A1 is a proper subset, or the ideal generated by A1 is a proper subset of the ideal generated by A2, and A2 has no factorization into irreducibles. Okay, so then I'll take A2 and I'll write it as A3 times B3, and I'll repeat the same argument and get that the ideal generated by A2 is properly contained in the ideal generated by A3, and I'll just keep continuing this way. I'll always pick the factor that can't be written as a product of irreducibles and factor that down. Okay, what does that give me? That gives me an ascending chain of ideals. I have that this ideal is properly contained in this ideal, which is properly contained in this ideal, properly contained in this ideal, so on and so forth. But what's the problem here? This is a contradiction since R is a PID and it satisfies the ascending chain condition. right? So we reach our contradiction here. We contradict the fact that PIDs satisfy the ascending chain condition. Therefore, we have that every element of R has a factorization into irreducibles. Every non-unit, non-zero element of R has a factorization into irreducibles. So now we'll clean this up and do the uniqueness portion of the proof. Okay, so let's do the uniqueness portion. So I'll suppose I have two factorizations into irreducibles, P1 times P2 times dot 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 times PR, and Q1 times Q2 times dot 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 times QS. Well, if I have this factorization, the first thing I'll note is that P1 ends up dividing Q1, Q2 up to QS, right? So what we're going to do is we'll reorder and relabel the Qs so that P1 divides Q1, right? I know that if P1 divides a product of elements, then P1 has to divide one of those elements. It's a slight generalization of the lemma we just proved earlier. But what does this tell me? If I have an irreducible that divides another irreducible, then P1 and Q1 are associates. And what does that tell me? That tells me that P1 is equal to C1 times Q1, where C1 is a unit. Okay, so now I can rewrite my factorization. I can say this is C1, Q1, P2, P3 up to PR is equal to Q1, Q2 up to QS. And since I'm working in an integral domain, I have factorization, so I could cancellation, so I can cancel those Qs, right? So what do I have? I actually have C1, P2, P3 up to PR is equal to Q2, Q3 up to QS. Okay, well, then what do I know? I repeat the same argument. I know that P2 has to divide Q2 up to QS. So after relabeling and reordering my elements, I get that P2 divides Q2, which means that P2 and Q2 are associates because they're both irreducible. So this tells me that P2 is equal to C2 times Q2, where C2 is a unit. Okay, so what does that tell me? Then I have C1 times C2 Q2, P3 up to PR is equal to Q2, Q3 up to QS, right? And then I cancel the Q2s, and I now have C1, C2, P3 up to PR is equal to Q3 up to QS, and I continue this way. Okay, so what do I notice? Well, if R is greater than S, then what am I going to end up with? If there are more elements on the left-hand side than on the right-hand side, I'm going to end up with C1, C2, all the way up to PR minus S up to PR is equal to 1, right? But this tells me that PR is a unit. So that's a contradiction. If R is less than S, so if I have more elements on the right-hand side, then I'm going to get C1, C2 up to CR is equal to Q times S minus R all the way up to QS. This is going to tell me that QS is a unit. So this is a contradiction. So the only possibility is that R is equal to S. And as a consequence, I see that, well, P1 and Q1 are associates. P2 and Q2 are associates all the way down. And so I get uniqueness from that. Okay, so that finishes our proof. Okay, so I just want to point out that the converse of this theorem is also false, and the examples are a little bit easier, but still kind of tricky, and again, will deserve their own videos because the proofs are a bit complicated. So Z bracket X is a UFD, and what's the main idea behind this proof? Well, the proof requires that we pass the polynomial from Z bracket X to Q bracket X and use the fact that Q bracket X is a UFD to get a unique factorization in Z bracket X. We know that Z bracket X is not a PID because the ideal generated by 2 and X is not a principal ideal. We can't find an element of Z bracket X that generates this ideal. Okay, and finally, this is a nice little summary of how all of these ideas in ring theory are connected. We have that every field is a Euclidean domain, but not every Euclidean domain is a field. So these implications don't go backwards, they only go forwards. We showed that every Euclidean domain is a PID. We've shown that every PID is a UFD. We know that every UFD is an integral domain because everything we did today was built on top of integral domains. And by definition, every integral domain is a commutative ring with identity. And again, we know that these arrows don't go backwards, right? So it's not the case that every commutative ring with identity is an integral domain. Consider Z mod 6. It's not the case that every integral domain is a UFD. It's not the case that every UFD is a PID, and so on and so forth. So these arrows go forward, and we have this nice little kind of summary of how these fit together.